Good afternoon. Uh, if you could say just if I'm audible and my screen is visible.
Yes, you are audible and the screen is visible, Mr. Banerjee. My name is Chaitanya. I'm pursuing PhD from IIP Vishakhapatnam.
Okay, thank
Uh,
you.
I'm sponsored candidate actually. I have 20 years of experience in oil industry. So please, we can proceed. Thank you.
Yeah, okay. Okay. Thank you for your introduction. Uh, every Sunday we meet here for this NPTEL live TA session. This particular online certification course, Technologies for Clean and Renewable Energy Production. I am Devarun Banerjee, a PhD PMRF scholar from Indian Institute of Technology, Delhi. So what we usually discuss is that the overview of the last week NPTEL course lectures, and then some sample problems we discuss. So in this particular week, the lecture one was all about the basics of petroleum and crude oil. What is petroleum? Origin of petroleum, uh, its availability, and how basically the energy production is carried out from petroleum, along with the types and grades of this. Apart from that, we get actually the energy and also the value added chemicals and all those things from as a petroleum products. So be it asphaltene, be it wax products, and apart from the energies. So this classification and its energy content, all those are all discussed in the first lecture. Apart from that, the composition of basic composition of crude oil was also overviewed. And also the how the basically the pricing of petroleum is actually varies, and what are the basically the parameters which affects the pricing of petroleum, and basics, the challenges and some issues of this particular utilization of petroleum for energy production from the perspective of the climate change, the CO2 emission, and other greenhouse gas production, especially when we are basically trying to target the renewable energy sectors. There is very important to understand that. So just quickly go through the initial uh, slides. So the basic contents of this particular petroleum and crude oil are majorly carbon, and apart from that, 10 to 14% hydrogen, and the rest of the very minor contents like nitrogen, oxygen, sulfur, and very less concentration of metals, less than 1000 ppm. So the basic difference is between this crude oil and petroleum is that petroleum is basically a broad category which includes both the crude oil and the products of the petroleum. So only the complex mixture of the hydrocarbons, which are basically these aromatics, paraffins and naphthens, which is basically brownish black in color and colloidal in nature, that is the uh, called the crude oil. Apart from that, the how by different theories, inorganic and organic theories, the petroleum has been originated by these millions of years by the heat and pressure. Due to this effect of temperature and pressure, the carbons which are generated from this inorganic sources or organic sources, these get transformed into the particular petroleum. uh, the different oil reserves distribution worldwide, and how this particular oil is distributed in between different types of oil, uh, like oil sands, bitumen, conventional oil, extra heavy oil, or heavy oil. So those are also discussed, and some general availability of petroleum overall worldwide, and how this basically the depletion we term this we talk about this thing about this kind of fossil fuels like coal and natural gas, petroleum, and all these things. Like this is reserves will be actually gradually decreasing. You can see that the projection beyond the 2010 or maybe 2020, it will be gradually depleting. Therefore, these renewable energy resources are getting more and more importance. Then the different types and grades of petroleum, light, medium, heavy oil, and different types of how we can actually uh, these are quantified also, based on this different sources. This the quantification is also very much important, but it gets varied due to the different sources, like Bombay High, Bonny Light, Arb Light, or Kuwait. These different sources are actually incorporating the fractions of the light, medium, or heavy distillates in this particular petroleum. Uh, Apart from that, the again the same things like the entire composition is also varying, uh, and also the different properties like this API gravity, pour point, ox content, all these things, these are also varying due to the different sources. So it has to be very much clear. Apart from that, the petroleum products, how these are actually the petroleum products, how these are basically gets distilled, and there's a refining from C1 to up more than C70, gradually depending on the temperatures. They are transformed into value-added products, and the valorization takes place in this way. And these different primary and secondary products, and depending on their uh, this boiling points, this basically distillation takes place. How much the easy uh, boiling point would be getting out as a lower temperature. Similarly, at the heavy gas oil and the other residues are having a very high boiling point, so need to reach the particular our reactor to that particular level of temperature. And apart from that, this apart from the hydrocarbons which are present in crude oil, there are also some non-hydrocarbons like this nitrogen, sulfur, oxygen, and some ppm levels metals are also present in our crude oil derived things. Now all these details are also discussed. The paraffinic components, the isoparaffins, naphthenes, aromatics. So and finally the pricing, how this particular pricing is actually varied, and the important factors behind this particular pricing of crude oil and petroleum products. So coming to the next one is that the second lecture, which actually was discussed in as the crude oil properties, the different impurities present in the crude oil, and how basically we can use different kind of estimation methods which will be giving the different kinds of parameters or the properties of this particular crude oil. In that also, the overall properties and the different impurities which are present in this particular crude oil, those are also discussed, like this density and API, degree API, reed vapor pressure, pour point, annealing point, wax content, and how basically this kind of wax content is estimated via this angular Holder method, which is basically based on the particular extraction technique. And also, apart from that, the carbon content, ash content, these are also discussed. Apart from that, the uh, percentage ash, and the salt content which are present in our crude oil, these are also overviewed. And the different methods, basic methods, which are standardized methods, basically the ASTM method or the IP method, which are used for the salt content determination, and also different metals which are also present. Those are also discussed here. As also mentioned, these metals and sulfur, nitrogen, oxygen, these are the basically impurities which are basically decrease the the calorific value and the octane rating of that our particular crude oil. So it is very important to identify which kind of impurities are there and maybe try to remove those particular impurities. So in that way, the different it was also categorized the sulfur content, the uh, total sulfur estimation, like you can use a ICP-MS or XRF technique to get sulfur content, but the very easy the common technique is the ultimate analysis, which we do also for the coals and biomass. So it will give us the CHNS, all these percentages. Similarly with the nitrogen also, finally the octane number and the cetane number was also discussed, and then the aniline point, diesel index, acid value, uh, the base value, viscosity, flash point, fire point, uh, softening point of hardness, all these different properties are also discussed. The third lecture discussed is the refinery flow sheet, desalting, atmospheric distillation, vacuum distillation, and the conversion processes. So in the general refinery, the preliminary task is to do the desalting and then to pass it out through an atmospheric distillation unit, and then for the further uh, purification or further product extraction, vacuum distillation is also carried out, and then its extract is also uh, passed through for further processes like maybe gasification or some other processes. So those are also discussed in the third lecture. And the fourth lecture was the need of conversion of intermediate products, the major conversion routes, which are basically via the carbon rejection route, which incorporates the thermal and fluid catalytic cracking process, via the hydrogen addition route, which means that the hydrogenation or hydrogenolysis, hydrocracking, this kind of steps are there. And apart from that, the reforming, isomerization, alkylation, polymerization, blending, those are all the other routes which are used for the further valorization of crude oil. So the requirement for the conversion of these intermediate products is basically that to improve the product quality, obviously, like and so when we are trying to meet a certain requirement in the market of these various products and to achieve a certain environmental standards, we need to convert them more and more this kind of intermediate products via these different techniques. The thermal and catalytic cracking is one of the most important techniques. Catalytic cracking and with thermal cracking, the difference is this is the non-catalytic process and this is a catalytic process. Obviously, when you're using the catalyst, the activation energy is getting lowered, and due to which the pressure and temperature range is getting lowered compared to the only thermal cracking. Basically, the decomposition of the large molecules to the smaller molecules, it takes place in the primary reactions, followed by the secondary reactions, where these different active products which are formed via these particular first reactions, primary reactions, those again further convert to form further lower product, or maybe some coupling reaction or polymerization reaction takes place to get heavy products. So we can get the upgraded products to polycarbonaceous products. So this in this particular cracking reactions, the fluidized catalytic cracking is one of the most important and famous reactions, where you can get this kind of different vacuum residue, vacuum gas oil, hydrotreated vacuum gas oil, coker gas oil. This kind of all these things are important for this fluidized catalytic cracking. And a simple way the conversion can be calculated, this feed minus LCO and divided by the what quantity of the feed you have fed into 100, the per for conversion into the percentage. and the different steps in the fluidized catalytic cracking. The basically the first initially the initiation steps takes place where the protonation reaction actually happens via this particular uh, via this particular the hydrogen sources where this H plus gets adjoined into this particular hydrocarbon, and then this hydrogen abstraction takes place where we are get these reactions can happen parallelly or maybe complementary to each other, and then when like via one of these particular steps you can get this particular protonated form either via this hydrogen abstraction or via this protonation. So after that this particular intermediate or unstable intermediate, it undergoes a hydrogen transfer or hydride transfer reaction. uh, the hydride transfer uh, is that for that the active sites of this catalyst are very important, where this kind of hydrogen would be dissociated and it would give giving us those hydrides. So one H2 will be giving 2H or hydrides. So those transferred hydrogenation reaction would be very important to convert this particular molecule into this kind of moieties, and then the fission reaction will be taking place where we will be getting one of those kind of bonds will be cracked via again on a catalytic surface, the catalytic active sites, so that we are getting this one of the moieties or one of the carbon space is different and the other carbonaceous portions as a different part. Similarly, some other reactions, more chemistry, is the isomerization reaction, where there is no addition or subtraction will be taking place, but just a rearrangement or kind of thing would be there. So instead of the carbonium at the secondary place, where it means that the carbon is attached to two other carbons, so it would be getting rearranged to the tertiary carbonium ion. It can also be happening. The cyclization to 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 minimize its free energy content, it can also happen, and further cyclization it can undergo alkylation, condensation, or again polymerization to get this kind of naphthenic structures, or maybe this kind of aromaticity generation, so that we can be getting a more and more valuable products. Uh, some of the factors which are important for this fluidized catalytic cracking performance are majorly the dependent factors, which are the regenerator temperature, catalysis circulation rate, the regenerator airflow. What kind of when you are talking about the regeneration, which means that there will be when you are this kind of hydrocarbon reaction, there will be always coke formation, coke deposition on this the catalyst surface. So the how much temperature we are actually putting our regeneration, and the how much catalyst we are actually get from this regenerator, and then again feed into our reactor. This is very important, and it would be obviously depending on how much coke deposition is there and what is the optimized value for the regeneration without destructing the original structure of the catalyst. And further the hydrogenation reaction, which means is uh, the implication of the hydrogen in the cracking in presence of hydrogen. What would be happening is that the coke formation, which we were talking about just earlier, that it would be actually mitigated during this cracking of high molecular weight, and will the constituent is the polar nature. So in that particular hydrocracking, the straight run gas oil, VGO, cyclyl oil, coker gas oil, all these are actually gets into the as a feed material, and via this hydrocracking unit, you get the LPG, the motor gasoline, the ATF, the diesel fuels, all these high value fuels, and other petrochemical based products, maybe some petrochemical polymers on the wax products, or some different solvents we such as THF, acetone, IPA, those kind of things, lube oils, all these things are we can be getting as a product. Some of the example of this particular hydrocracking reaction are given here. So in between, inside those hydrocracking reactor, the different reactions which can actually take place are the hydrogenolysis, hydrogenation, hydro dealkalization, hydroisomerization. So when you are talking about this hydro terminology, which means that the presence of hydrogen is always important and is there for all these reactions. So and apart from that, the catalyst which are actually used, so in this particular hydrocracking unit are usually the noble metals, the platinum, palladium. Apart from that, non-noble metals, molybdenum, tungsten, nickel, cobalt, uh, all these types of different non-noble metals can be used. The important thing is that the utilization of noble metals generally requires the low quantity. So when you are taking a support, maybe a zeolite or silica or maybe alumina, those kind of support, loading a particular metal to give out the desired activity, the requirement of noble metal will be less. But still that 1% or maybe this less than 1% noble metal would be enough to to make you think that how are we going to get that much of cost from this particular reaction. On the other hand, we'll be giving a more quantity of non-noble metals, uh, like 2 to 8% for nickel cobalt or 12 to 30% for molybdenum and tungsten and oxides. So greater quantity of this kind of non-noble metals are required. However, the activity and these things, the product yields are important to judge how much actually we are getting, and also not, by not getting deactivated. Uh, these is the major things which have been discussed in this particular overall lectures. So, and then we'll try to move on to the different sample problems which are there. So the first question is that you have to identify the operations P, uh, Q and R in this particular flow sheet. So you have to tell that whether this is a atmospheric distillation unit, vacuum distillation unit or desalter, or maybe a steam reforming unit, adsorption or distillation unit there. So in this particular crude oil refining steps, it is the correct answer is that the first you have to do the desalting operation of the crude oil, and then giving some temperature by in the vapor phase you have to feed it into the atmospheric distillation unit, and then the more uh, boiling point fractions will be putting into the vacuum column. The vacuum residue would be getting into which are actually get boiled more than at 540 degrees Celsius. So this vacuum residues would be fed into the vacuum distillation unit, which the residues from this particular vacuum distillation unit we get into the for further processing, like for gasification, or for we'll be getting the heavy lube oils, bitumen, or all this fuel. So the correct answer would be this would be the desalter, this is the atmospheric distillation unit, and this is the vacuum distillation unit. The performance of desalting operation is affecting by which of one of the following parameters. So it's the settling time, demulsifier injection, effective mixing of oil and water as well as chemicals, or is it all of the above? So the correct thing is that this all of the above answers are correct. So the important variables which actually affect this desalting performance are obviously the settling time, the how much injection we are giving to the demulsifier unit, and apart from this, the how much heat we are providing, uh, the recycling loss of the fresh water. So how much fresh water we are giving into the desalter, all these particular things matter. So all of these options are correct. Uh, Now the next question is that the electrostatic attraction between the droplets, which it can be represented as this, right? So you have to tell that what is the correct answer. So the correct answer is that the electrostatic attraction force is that the K is the dielectric constant, and it's basically the force. What happens is that is proportional to the square of the voltage gradient and the sixth power of the diameter of the water droplets, and it's inversely proportional to the center to center distance between these two adjacent droplets and to the power 4 of it. So the correct answer would be the F equals to K E square D to the power 6 divided by S to the power 4. And the important thing is that you have to see here also that at a particular voltage also the water droplets they tend to rupture, and automatically the larger droplets will be forming a smaller droplets, and obviously the interfacial tension which is there in between this surface tension, those gets increased, which means that the emulsion which is actually getting formed will be more and more stable, so decreasing the size. So this this voltage gradient you can actually define it via this surface tension that I was talking about, and via how much this is the diameter of droplet. So it's directly proportional to this particular surface tension and diameter of droplet, the ratio of both these two and the square root of this particular ratio. So the another next question is that the degree API gravity of natural gasoline and kerosene are 65 and 48 respectively. So you have to determine the specific gravity difference between them. Was it is 0.16, 1, 0.29 or 0.068. So the correct answer is that it's 0.068. So uh, to check the density, how we actually try to represent it's the ratio of the mass and volume, and specific gravity is just basically a uh, again a ratio of basically density of whatever the sample we have, and corresponding reference density of water. So this is called a specific gravity, m by v of sample by m dash by v dash water. And the degree API which we can get is utilizing this specific gravity, and it should be measured at the 60 degree Fahrenheit, and using this particular formula we'll be getting the degree API gravity is 141.5 by divided by specific gravity of 60 by 60 degree Fahrenheit minus 131.5. So if you utilize this particular formula, you have to put the value of degree API which is given here for natural gasoline is 65. So 65 equals to 141.5 divided by specific gravity minus 131.5. So to put this, take the specific gravity to the left hand side, and it would be like 141.5 by specific gravity of gasoline equals to 65 plus 131.5 equals to 196.5. So again, doing the other mathematics is the specific gravity would be 141.5 divided by 196.5 is 0.72. And the similar, exact similar way to take the kerosene API, which is 48, is given. Put the value, take the specific gravity. On the left hand side, it will be 141.5 by specific gravity of kerosene equals to 48 plus 131.5, and ultimately specific gravity of kerosene would come out as 0.7883. So the difference between both of them will be 0.7883 minus 0.7201 equals to, is the correct answer, 0.0682 is the difference between their respective specific gravities. And apart from that, in there, there's some other examples of this degree API are also given, as water having a 10 API gravity, kerosene having greater API gravity as 45, motor gasoline, natural gasoline, which are having 58 and 75 APIs respectively. Now the next question is that what is the typical carbon percentage in the crude oil? Is 53 to 63%, 53 to 73%, 43 to 57%, or 83 to 87%? So the correct answer would be about 83 to 87%. As already mentioned, that the crude oil having a large quantity of carbon, about very closer to the anthracite nature of coal. So it's about 83 to 87% carbon it is having. Apart from them, the rest components are hydrogen, nitrogen, oxygen, sulfur, and some ppm levels metals. Uh, so therefore, the correct answer would be like this: it's 83 to 87 percentage. The next question is that the medium oil uh, medium oil API gravity is what? Between 12.3 degree to 22.1 degree API, between 22.3 to 31.1 degree, 32.3 to 41.1, or it's 42.3 to 51.1 degree API. So light crude oil, medium crude oil, and heavy oil. These are actually based on this their difference in density or degree API gravity. They are actually classified. So the light crude oil is having a higher degree API, which is more than 31.1 degree API. The medium oil is having an intermediate range between 22.3 and 31.1 degree API, and heavy oil having a lower degree API gravity, which is 22.3 degree API and below that. So medium oil is having this in between range between this 22.3 degree and 31.1 degree API. That is the correct answer, between 22.3 degree and 31.1 degree API. What are the influencing factors for crude oil pricing? These are already discussed in initial uh, slides. The supply, demand, political or economic developments in the exporting or consuming countries, or weather conditions, or all of these. The pricing of the crude oil is important because of what? Supply, demand, political or economic developments in the exporting, consuming countries, or weather conditions, or all of these. So the correct answer is that the crude oil price actually is varied due to all of these particular factors, like supply and demand fundamentals, the political economic developments in exporting or consuming countries, and again also weather conditions. So apart from that, also the OPEC, the Organization of Petroleum Exporting Countries, uh, which include the Middle East countries like Iran, Iraq, Kuwait, Saudi Arabia. This all the policies that they make this particular uh, entity uh, of their collaboration. This kind of oil exporting Middle East countries. So these policies are also important. So all these factors are very important for the crude oil pricing. So now the slightly numerical problem, analytical problem is that to break the water and oil emulsification in crude oil, an electric field is applied during desalting operation, right? So so that the salts will be get removed. So the force of attraction between these water droplets would be varied if the electric field is increased to 8 times of the previous value, and the diameter of water droplets should be reduced to the half of the previous value. So what would be the particular thing you have to tell me? So the force of attraction between these water droplets, how would it be varied? It would be increased by 4 times, it would be decreased by 4 times, increased by 16 times, or it would be remain as it is. Remember, there are two factors which are being varied simultaneously. Is that the electric field is varied 8 times of the previous value, and similar fashion, the diameter of water droplets are gets reduced to the half. So the correct answer is that it would be getting unchanged. How is it happening? You have to take this particular formula. Is that the force of attraction is directly proportional to the E square d to the power 6 divided by x to the power 4. So K is the dielectric constant. So E square is that particular electric field between these particular two water droplets. D is the diameter of it, and S is the center to center distance. So it is telling us that its electric field and the diameter, these are varied. So you can take this K by S to the power 4, this particular entity as constant. So K by S to the power 4 taking as constant, and giving us the F1 and F2 are this particular force of this particular two water droplets. So K by S to the power 4 into multiplied by E1 square D1 to the power 6. This is the first one, F1, and the second water droplet force of attraction would be K by S to the power 4. This is the same for both of the water droplets. The variation is here, E2 square D to the power D2 to the power 6. Now what they have told is that electric field is increased 8 times, which means that E2 would be 8 times of the E1, and diameter is reduced to half. So D2 would be half of D1. So putting these values in this particular F2 formula, F2 would be K by S to the power 4, 8 E1 whole square, and D1 by 2 whole to the power 6. So 8 square means 64, and 2 to the power 6 means also 64. It would be 1 by 64. 64 would be getting cancelled and would be getting a same value as a F1. So F1 would be equal to F2. So it would, the correct answer would be the force of attraction between these water droplets would not be varying, it would be remaining unchanged. Now have to match the petroleum products. These are all these petroleum products: wax, petroleum coke, asphalt, with their respective applications. Coal-fired boiler, roads, roofing material, candles, industrial sealants. Have to match like this: PQR and as 1, 2, 3. What is the correct one? P2, Q3, R1, P3, Q1, R2, or P2, Q1, R3, P3, Q2, R1. So even if you don't know all this application. You can easily just getting like wax. We know that it is used in making the candles. So automatically wax will be connected to the candles. So there is P3. However, P3 will having two options. So it's P3 Q1 R2 or R1. So R is asphalt. Asphalt we know asphalt is used heavily in the road formation, road making. So R will be definitely going with the R2. So P3 R2 there is only one option. So even if you don't know one of these answers, you can make the answer of this kind of problems. So you can see here there all of these are as a part of the secondary products by this petroleum refinery, where the kerosene uh, we know as a home heating, this kerosene lamp as a charcoal fluid, and the LPG as a chemical feed we use as a application to cook and all these things, the heating purpose also. The fuel oil we all use as a in the furnaces, boilers, ships, and some in some cases of home heating. Asphalts we use in the roads, roofing materials, sealants. Carbon black oil for definitely based on this carbon. So making this carbon based things, the tires, carbon composites, and carbon black. Uh, Lube oil is to get the lubrication things, to get the fluidity, to reduce the friction between the engine and machinery, mechanical things. Waxes we try to make candles and industrial sealants. And apart from that, petroleum coke, the coal fired for making the coal fired boilers. Metals, metals means this anode and cathode, those things are utilized here. The next one is that the same amount of aniline and a lube sample is heated under specific condition, and these are mixed at 110 degrees Celsius. By mixed, it means that they are miscible at 110 degrees Celsius. So if the specific gravity of the lube oil is 0.9, so you have to determine the diesel index of the oil. It's 45, 59.16, 63, or 36.9. So the correct answer is the 59.16. So you know the diesel index formula is that the degree API into aniline point in degree Fahrenheit divided by 100. So you have indirectly it has given us actually the aniline point. It means that a same amount of, it means that 1:1 ratio, a particular sample and aniline, if you heat it under specific condition and you see that these are miscible at under certain temperature, it is actually the aniline point of this particular sample. So the aniline point here is by the mixed, it means that they are miscible at 110 degrees Celsius. So 110, if you put just you have to convert this degree Celsius into the Fahrenheit. So we know that C by 5 equals to F minus 32 by 9. So from that you have to take the F, which means that C, which is 110 into 9 divided by 5 plus 32, would be giving us a respective Fahrenheit. The aniline point of this particular loop sample would be 230 degrees Fahrenheit. Put this particular aniline point value, uh, have to put this in diesel index, but still we are having one another unknown, which is the degree API. For determination of degree API, you have been given a specific gravity value, which is 0.9. So to again put this old formula 141.5 divided by specific gravity at 60 by 60 degree Fahrenheit minus 131.5. So putting this specific gravity value here in this formula 141.5 by 0.9 minus 131.5, we getting to for 25.72. So this degree API 25.72 into 230 divided by 100, you'll be getting 59.16 as the correct answer as the diesel index of this particular lube sample. So the techniques by which the crude oil is separated, which it is known as sublimation, decantation, fractional distillation, crystallization. Very simple question is definitely the fractional distillation, based on the temperature. Have to gradually separate these different components uh, between the very like volatile gases from 20 degrees Celsius up to more than 600 degrees Celsius, they can be separated, and along with this based on this carbon number would be increasing towards this based on this particular boiling point, and they're also increasing in density also. So this is a fractional distillation we are using for this particular crude oil separation in the refining process. The Reid vapor pressure indicates the relative percentage of gaseous and lighter hydrocarbons in the crude oil. So the Reid vapor pressure value for butane is 14, 94, 34 or 40 psi. What is the correct answer? The correct answer is 94 psi. The Reid vapor pressure is already told in this particular question that it gives us the percentage of the gaseous and lighter hydrocarbons in the crude oil. So you can see that butane is having a 6.6 kg per centimeter square Reid vapor pressure. We have to convert it to psi, and we will be getting this 94 psi as the Reid vapor pressure value. So is the particular factor of about 14.24, you have to multiply, and we'll be getting this particular answer. Next question is that the what structural features of hexane uh, contributing to the lowest octane number among these all these things are shown here. These different compounds is hexane, cyclohexane, benzene, and 2,4 trimethyl pentane. You can see there's a hexane having an octane number 25, cyclohexane having an octane number 83, benzene having an octane number 100, this 2,4 trimethyl pentane also having an octane number of 100. But why hexane having a lowest octane number among these particular sets of compounds? Is it because of hexane has a straight chain? Is it because it doesn't contain oxygen? It doesn't contain lead, or it contains a ring structure? So it is very obvious hexane doesn't contain a ring structure. We all know this. So it also doesn't contain a lead, but so as the other things also. Again, when you're comparing that, neither these or them, nobody contains any oxygen also. But so the simple separation factor is that the hexane has a straight chain, but cyclohexane, benzene, they are all the cyclic compounds. Cyclohexane is not an aromatic, but benzene is an aromatic compound, and this is also another 2,4 trimethyl pentane, but this is having a greater octane number. So hexane, due to having a straight chain, there is no electron cloud, right, like in this particular uh, aromatic compounds, or uh, due to that the octane number on the knocking anti-knocking effect is very less for the NXF. The equivalents of aniline and diesel oil when mixed at room temperature are found to be completely miscible. So it means that the aniline point of the diesel is similar to the room temperature, or it would be less than room temperature, more than room temperature, or it can be either of them, either more or less than the room temperature of this particular diesel oil. So the correct answer is that the similar to the room temperature. It's already discussed that when these equal volumes of the aniline and particular sample, it gets miscible at a particular temperature. So this particular temperature would be called as the aniline point of the sample. So when this particular diesel oil is getting mixed with the aniline as a room temperature, so we'll be calling the room temperature, whatever this ambient temperature 20, 25, 30, by record of that particular room temperature would be the same as the aniline point of the particular sample. The hydrocracking, which is carried out in the presence of hydrogen, already discussed. So we have to tell that what is this process carried out under which kind of conditions. It's high pressure and low temperature, high pressure and moderate temperature, low pressure and high temperature, low pressure and low temperature. So when you're talking about this high and low, this kind of terminology, it is basically happens because of this comparative study between the FCC and hydrocracking. So and see that the FCC actually happens at the uh, low operating pressure, whereas the hydrocracking happens as a very high, about 1500 to 2800 psi pressure, whereas the temperature required for the hydrocracking is actually moderate, not very low, but not very also high, so about 600 to 780 degree Fahrenheit. Whereas for FCC, the fluidized catalytic cracking, the operating temperature is very high, is about 900 to 1000 degree Fahrenheit. So it would be uh, the correct answer would be the high pressure and moderate temperature. Uh, Another question is that during the desalting process after coalescence, the water droplets containing salt settle down in a desalter. So the settling rate of this particular droplet should be changed if the viscosity is reduced to one third times by the increasing temperature. So directly cannot change property like viscosity of this particular water droplet. You have to change it via varying some factor, some controllable factor. So here the changing the temperature, the viscosity of the water droplets are getting changed. So to tell the what is the effect on the settling rate of these droplets by variation of this viscosity, would it be having causing no change, double, triple, or nine times? Yeah, you're correct. It's the triple. So basically, the Stokes equation we try to use for with this kind of problem would be having the downward velocity of this or the settling velocity of this water droplet. V equals to 2 r square delta rho by into g divided by 9 into viscosity. So all these other factors if remain constant, the viscosity is changing. So it's only the eta 2, the viscosity of the second droplet would be one third of the viscosity of the first droplet. So simple, it would be inverse. So the settling rate is getting changed by the inverse. It is in you can see it's inversely proportional to the viscosity. So it would be triple. So V2 would be 3 V1. So all the other factors 2 R square delta rho G 9, all these factors are constant for both of these cases. So it will be V2 equals to 3 V1. So these are all the questions we had to discuss. Apart from that, I would like to also discuss the tutorial question problems which are discussed in this particular week, just a revision thing. The first problem which are discussed in the tutorial, the degree API gravity of natural gasoline and kerosene are 75 and 45 respectively. The difference in the specific gravity, with what is that? Already discussed this particular problem, that have to just keep this particular formula. API degree API is 151.5 by specific gravity at 60 degree by 60 degree Fahrenheit minus 131.5. You have to just use this particular formula and get the specific gravity when the degree APIs are given, and then just subtract both of them. Will be given you will be getting the difference between the respective specific gravities. The second problem, uh, same amount of aniline and lube sample is heated under specified condition. These are mixed at 80 degrees Celsius. The specific gravity of lube oil is 0.88. Determine the diesel index of the oil. Again, this problem was also discussed with some other values. But the same thing, they have to use this particular formula of diesel index, aniline point into degree API divided by 100. So the aniline point uh, is given as 80 degrees Celsius, converted to the Fahrenheit is 176 degree Fahrenheit. The degree API, for the degree API determination, I have given the specific gravity. Utilize this formula to get the degree API. So it will be 29.3, and then use both these values, 176 into 29.3 divided by 100 would be the diesel index of this particular lube sample. Now another question is that to break the water in oil emulsion in crude oil, electric field is applied during the desalting operation to remove the salts. So how would the force of attraction between the water droplets uh, varies if the electric field is increased to thrice the previous value? So this similar problem was already discussed, where we actually found there will be no change because I think in that problem there were two factors were simultaneously varied, but it is much simpler. Uh, Here we'll be getting the attractive force will be becoming the 9 times of whatever was there originally. The fourth problem is that during desalting process after coalescence, the water droplets containing salt settle in down in a desalter. How would the settling rate of the droplets change? The viscosity is reduced to half by increasing the temperature. The same problem was also again just now discussed. So if this directly inversely proportional with the viscosity, so the temperature is increased to decrease the viscosity to half its previous value. The settling velocity would be just inverse of it. It would be getting doubled. The degree API of West Texas Intermediate crude oil is 39.6. So what would be the volume of 1 metric ton of this particular crude oil in barrel unit? So you have to remember this particular thing, one barrel, it means that 159 liter, and again utilize this particular formula of specific gravity equals to 141.5 divided by degree API plus 131.5. Original formula was to determine what API gravity equals to like that, but just transformed it to get the specific gravity from this particular value. So in this way it will be getting specific gravity as 0.83, and then putting this particular value, will be getting the volume of 1 kg oil will be nothing but 1 by divided by the specific gravity, which is 1.2 liter, which means that 1 kg oil having a 1.2 liter of volume, and this 1.2 liter volume means it is just converted towards the barrel. So one barrel is 159 liter, so to convert it to the barrel, so it's about 1200 divided by 159 barrel, which means that 7.55 barrel. Uh, the problem number 6 in this tutorial was the Watson characterization factor and the US Bureau of Mines correlation index are used to determine the aromaticity and paraffinicity of an oil. They calculate the Watson characterization factor in this way. Uh, so calculate the Watson characterization factor and correlation index for NPTEL, where this particular normal boiling point and the specific gravity are also provided. You have to remember this particular formula of Watson characterization factor, which is normal boiling point to the power 1 by 3 divided by specific gravity measured at 60 degree Fahrenheit. So why this force of 60 the addition is getting take place is to convert this particular value of degree Fahrenheit to Rankine scale. You have to add 460 to 97 as specific gravity is given. So Watson characterization factor is coming out as 13.06, and the correlation index having as this particular formula of 87,552 divided by normal boiling point plus 473.7 into the specific gravity minus 456.8. It means that the correlation index would be putting this again in a formula. The values in this particular formula 97 plus 460 for Rankine scale conversion, 473.7 into the specific gravity is 0.63 minus 456.8, which is coming out actually 0. So the correlation index of 0, it means that it's having a straight chain paraffin, and more it moves towards the aromaticity, we gradually going towards the CI value of 100. Similar thing is that the Watson characterization factor is we are having a 13.06, which means that when is having a 10.5 12.9 for paraffinic based crude, which is more than 12.9, so absolutely straight chain paraffin. As less than 10.5, which means that it would be highly aromatic. So it's directly paraffinic thing. Another problem was discussed, which is the catalytic reforming plant. produces hydrogen and benzene from cyclohexane by hydrodearomatization. In order to increase the production of hydrogen, the owner plans to change the process to steam reforming of the same feedstock, which produces hydrogen and CO2. So initially there was a catalytic hydrodearomatization was taking place. Now what he wants to do is that is the steam reforming process. So to know the stoichiometry, so using a cyclohexane, so directly hydrodearomatization, which means that it will be producing hydrogen, and how it will be producing hydrogen, these particular single bonds or the unsaturated bonds would be getting the saturated bonds would be getting an unsaturation. This is so cyclohexane will be converted into benzene and will be giving a 3 moles of hydrogen, and the other process is the steam reforming of this particular same feedstock, which means that you can see steam reforming the same feedstock, which means steam reforming of cyclohexane. So if we add steam with the cyclohexane, we're getting again the uh, similar feed with the oxygenated compound, but we'll be getting a more and more hydrogen because we're giving extra hydrogen as a feed also in the steam as a in the form of steam. So this stoichiometrically the ratio would be 18/3, which is 6. Another problem is that a gasoline mixture is formed by mixing different types of compounds, which is provided in this following table. We have to determine the requirement of N-butane to make this gasoline with read vapor pressure of 10. A very interesting problem that we have a mixture of this kind of different compounds, LSR gasoline, reformate, alkylate, FCC gasoline, which are having a certain mole per hour feed. So have to determine that and also the read vapor pressure of these each compounds are given. So how much quantity of N-butane would be required to make this particular mixture of having an entirely read vapor pressure of 10. So for that what we have to do, the initial read vapor pressure of this particular mixture we have to determine. So for that, it will be just the moles into read vapor pressure of each component. So it would be like mole per hour, so 457 into 11.1 plus 617 into 12.8, 295 into 4.6 plus 810 into 4.4. So that is the thing we have done. They have done divided by the original gasoline mixture, which means that the total summation of this particular mole per hour, the total quantity. 457 plus 617 plus 295 plus 810. If we add them, we will be getting 2179. So, and equals to what is the read vapor pressure of this original mixture coming out? Is a 5.38. So we are having a lower read vapor pressure original gasoline mixture. So we need to mix some N-butane in this particular thing, so that our read vapor pressure gets increased to 10. So how much quantity of read vapor pressure will be mixing to this? So it will be again similar kind of formula we will be using. So M1 into read vapor pressure plus M2 into read vapor pressure. So 52 is the read vapor pressure of this N-butane, right? So 2179 is the total mole of our mixture into 5.38 is the RVP of this, plus M is the unknown feed of N-butane into 52. This is the M1 RVP1 plus M2 RVP2 equals to what would be happening, equals to the total mole, which is the 2179 plus M into, we know that our target is to make a RVP of 10. So just solving this particular simple equation will be giving us M equals to 240 moles of N-butane. And again you can just transform into this mole per hour to the pound per hour, and further transform into the barrel per day also, which is coming out as 1640 barrel per day. The last problem is that how much heat is required to raise the temperature of 1000 pound of a 40 API mixed base oil from 100 to 600 degree Fahrenheit. So what is, and for that, to solve this particular kind of problem, we have given a chart. So the temperature versus the specific heat. So how to solve this kind of problem is a very simple. The MCPDT is a basic formula. So we have to determine the CP from this particular chart. So we are getting as two temperatures. We don't know the specific heat of this particular base oil, the 40 API mixed base oil, or this particular two temperatures. We have to determine from this chart. So at this six, it is 40 API, which means this line would be there. This 40 API at 600, it is coming out at around is coming out around between zero point 0.7 and zero point 0.8, right? Is about 4.775. The similar thing as a 100, so 100 degree Fahrenheit as the 40 degrees 40 degree API is coming out in between the, is less than the uh, just below the zero point 0.5 specific CP, so it's around 0.48. So what we have to take this, the average specific heat, so it will be just summation of them by 2. So 0.48 plus 0.775 divided by 2, coming out as 0.627. So you'll be using this M. This will be M, and uh, this is the average specific heat which are getting is the 0.627, and this is the DT, which is the 600 minus 100. So MCP DT will be around 313 313,500 British thermal unit. Okay, and also it's important to note that this whatever this average value we have taken between 100 and 600 is actually the same specific as 350 degree Fahrenheit. So if you just take the both this temperature average, is 100 plus 600 divided by 2, which means the 350 degree Fahrenheit, it will be coming out is 200, this is 300, this will be 350, right? So if you see, yeah, this is the 351. So you can see that yeah, it's around here. So it's about 0.627. So you just need to take the you can also take the average of this both this temperature and just determine the specific heat at that average temperature also. That would be coming out as the same of this particular specific heats of these two temperatures, and then uh, doing the average of that. So that's all from my side today. If anybody has any problems or concerns, please ask, or we will disperse.
Once again.
Okay then. Uh, so
Hello. Hello.
yeah, you're audible. Please.
Yeah. Problem number 8. Can you please go to the problem number 8, which you just explained? 8.
Yeah.
Let the moles of N-butane, which is required, no? You have a
Hmm.
LHS side from the earlier 2179 total moles into 5.38. 5.38 will be the actually it's a mole fraction, no? Already. They're little confused. Can you go back and can you please explain again?
The 5.38 would be the reed vapor pressure of this particular our mixture. Okay. So
Okay.
how we are getting it? just the number of moles multiplied by the read vapor pressure of each component and the summation of it. So if you just do it like 457 into 11.1 plus 617 plus 2 into 2.8 plus 295 into 4.6 plus 810 into 4.4. So this will be this right hand term. Okay. So and
Okay.
then divided it by the total moles in the blended product. The total moles is coming out this summation of this particular column. So it is 457 plus 617 plus 295 plus 810. So it is 2179. So you just do this right hand side thing and then divided by 2179, you'll be getting the 5.38, which is the read vapor pressure of this particular mixture. Okay.
Mm, here, sorry,
Hmm.
and the sigma value is there, no? I is equal
Uh-huh.
to one read vapor pressure into individual
Hmm.
component.
Hmm.
So in that, if I assume next n-butane is added, okay,
Hmm. Hmm.
already 5.38 we have that figure plus n-butane into its individual read vapor pressure is
Yeah.
equal to total moles into 10. That side is
Yes.
okay. 217 plus 9 plus m into 10 is okay.
Hmm.
But this 5.38 plus it should come, no? There actually I'm not able to catch it.
No, no. See, this 2179 is you are having this particular moles, okay? This
Earlier.
mixture, yeah, earlier, okay? So it is
Hmm.
again the same formula. The M into RVP. Now you have two components. One is N-butane, one is this mixture. So this
Hmm.
mixture RVP you have determined 5.38 into its total mole 2179 plus 52 is the RVP of N-butane into the total moles of N-butane. We don't know it yet.
Okay. Okay. So 5.38 is the RVP of total moles earlier, you are telling, right?
Yes, yes, this is the mixture what you have provided in the problem.
Okay. 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 Thank you. Thank you.
Okay,
Thanks for your.
okay, okay then. So we'll wrap up the session in this juncture. Anyway, any problem, any concerns, will we again try to meet on the next class, or meanwhile you can post it on this particular forum of this particular course also. We'll be getting all your doubts cleared.
Okay. Thank you.